Okay, so looking at 9.7, we're just going to look at factoring a couple special cases of trinomials or binomials. So we've seen factoring when our a value is 1. We've seen factoring when our a value is not 1, where we need to maybe do a little bit more work with the x box. Today in 9.7, you're just learning some new shortcuts for a few special cases. In general, everything from 9.6 and 9.5 will work the same, but if you can use these shortcuts, it can save you some time in the long run. So it's just a couple special cases. So let's look at the first case. Let's just start by factoring x squared plus 10x plus 25. Well, our a value here is 1, so we can do our nice easy factoring of asking what two numbers multiply to 25 but add to 10. And the answer here is 5 and 5. 5 times 5 gives you 25, 5 plus 5 gives you 10. So x squared plus 10x plus 25 is just x plus 5 times x plus 5. And if you're taking x plus 5 and multiplying it by itself, you can just rewrite this as x plus 5 squared. Because we know when we square something, that just means multiplying it by itself. Well, now thinking back to 9.3, 9.3 we started with something like this, x plus 5 squared, and ended up using our special case of multiplying to get something like this, x squared plus 10x plus 25. So we're really just using that idea and going backwards. So here we have that the perfect square of a trinomial pattern is if you have something that looks like a squared plus 2ab plus b squared. So a in this case would be 1. 1 squared plus 2ab, so 2 times 5 times x, plus b squared, 5 times 5. You can just simplify that right away to just a plus b squared. So just x plus 5 squared. You're just working backwards. And once again, if you don't love this idea, I know this can be confusing to memorize, don't even worry about it. Worry about just knowing how to factor this. If you can factor x squared plus 10x plus 25 and do this process, that's totally okay. But if you recognize that the shortcut is here, it can save you some time. Now let's look at another example once we know this rule. We have 3x squared minus 30x plus 75. Now you might think, okay, we got to do the x box. We have to multiply 3 by 75 and then find two numbers that multiply to that but add to negative 30. But don't forget to factor out a common monomial if you can. Notice 3 goes into 3x squared, 3 goes into negative 30x, and 3 goes into 75. So we can factor out that 3 and we're left with just x squared minus 10x plus 25. Now this looks fairly similar to what we had here, only now we have minus 10x. So using our special pattern, we can notice that our a value is just x squared. Our b value, if our a value is x, our b value must be negative 5. And that would work over here too, because if you have negative 5 times negative 5, that's going to give you 25. So using our shortcut, this is just going to be x minus 5 squared. So if you can recognize that a is x and b is negative 5, it can make this factoring process quite a bit faster. Now let's look at another example of a special pattern that looks a little bit different, and this one is used very, very frequently in mathematics. So how would we factor something that looks like m squared minus 9? Well, it might not be super obvious right away, but let's ask this question. Could we rewrite m squared minus 9 as m squared plus 0m minus 9? 0 times m is just 0, so really this doesn't mean much, but this can help us look at how to factor this. Now we're looking for two numbers that multiply to negative 9, but add to 0. And you'll find pretty quickly that two numbers that multiply to negative 9 but add to 0 are just 3 and negative 3. So to factor this, we have m plus 3 times m minus 3. And that's our factored form. So our rule here, if you're looking m plus 3, m minus 3 to get to m squared minus 9, our rule is what we call the difference of two perfect squares. So if you have something squared minus something else squared, that's equal to the first piece plus the second piece times the first piece minus the second piece. The idea with m squared minus 9 is that this is the same as m squared minus 3 squared. 9 is a perfect square, m squared is a perfect square. So looking at our next example here, we have 4x squared minus 25. Well, 4x squared is just 2x squared. 25 is just 5 squared. You don't need to include this step, but I'm just going to write this in to show you how we get down here. We can now just take a plus b times a minus b. A in this case is, A in this case is just 2x. And b is 5. 2x plus 5 times 2x minus 5. And we're done rather quickly. Looking at our third example now, what times itself gets you 49? Well, 7. So our a value is 7x. What times itself gets you 81? 9. So we have 7x plus 9 times 7x minus 9. And remember, you can always check your work. If you were to FOIL this, you'd get 7x times 7x equals 49x squared. If you take your inside term, you'd get 63x. Outside, you'd get negative 63x, so those would go away, and you'd be left with minus 81. This is a very, very nice shortcut, this difference of squares, that you will see very often. Okay, so let's use these methods to solve. X squared minus 16x plus 64. Now here's one of those situations where we're saying, okay, it's not going to be difference of squares, so we might want to look at our other shortcut. So if you have a squared plus 2ab plus b squared equals a plus b squared, you can use that shortcut. But once again, ladies and gentlemen, if you forget that rule, just factor this like you'd normally would. What two numbers multiply to 64 but add to 16? Well, negative 8 and negative 8. So the idea is you're taking x minus 8 times x minus 8, which is just going to be x minus 8 squared equals 0. So if x minus 8 squared equals 0, x would have to be 8, because you need something times itself to get you 0. The only way that could be true is if the inside of here is 0, so 8 minus 8 gives you 0. So our solution is x equals 8. Let's look at this one. Looks kind of nasty on the surface. Well, to solve this, we would first want to get this in standard form. So we might subtract 3x from both sides. And we might subtract 10 from both sides. When we do that, we get 81x squared. 3x minus 3x, the x's will go away, minus 25. Well, now we see a binomial, 81x squared minus 25. Well, this is a difference of squares because 81x squared is just 9x, that whole quantity squared, minus 5 squared to get you 25. So we have 9x plus 5 times 9x minus 5 equals 0. So now we have to do a little bit more work to solve. We're going to have 9x plus 5 equals 0, or 9x minus 5 equals 0, and we'll solve each of these for x. So we have 9x equals negative 5, so x is negative 5 ninths, or we'll have the opposite, 9x equals 5, so x equals 5 ninths. So we get two solutions for this equation. Once again, if you're ever concerned, I don't know if I did this right, this fraction doesn't look very nice, just plug it back in. Plug it into your equation, see if you get something that checks out. that wraps us up for 9.7. It's just a couple more shortcuts. The difference of squares is the bigger one here, because if you do forget this first special rule, this first perfect square trinomial pattern, it's not a huge deal because you can always just factor and then you just have the one more step to rewrite it. But the difference of squares is something that you will definitely want to know and want to memorize for your mathematical endeavors moving forward.